This is the last lecture of this quarter in physics, and we're going to end this group of physics lectures with a discussion of uniform circular motion. Uniform circular motion is defined as motion that occurs in a circular path at a constant speed. That means that the magnitude of the velocity around this path does not change. And I'm emphasizing that because although the speed is constant, the velocity is not constant because the direction is constantly changing. And we will talk about that in more detail in the next few slides. In order to understand or discuss uniform circular motion, we have to talk about something called the rotation angle. The rotation angle is the amount of rotation that occurs at any particular time and is analogous to, but not the same as, linear distance. And so it is the amount of angle that is subtended or moved as one moves around this outside of this circumference here. So this rotational angle, delta theta, is this amount of movement. It is analogous to displacement, but it is not the same. So delta theta is equal to delta S divided by R, where delta S is the length of this arc right here. And R is the radius of the circle, or radius of curvature. So delta S is a line that you would draw if you had a compass or something of that nature. And the angle here is going to be equal to that line, the length of that line, divided by the radius. And this is, I'm going to circle throughout this equations I think that you will use while you're working your problems. And so those are equations you should take note of. Now the arc length, which is the linear distance, is the linear distance from point A to point B, and it's also called delta S. The radius of curvature is this linear distance from 0 to A or 0 to B. And so again, the angle of displacement or rotational angle is delta S divided by R. So let's take a look at some properties. For example, you have one point here rotating to here, one point here rotating to here. Now it appears as though, and they do travel through the same delta theta. However, the delta S1 is less than delta S2 because R1 is less than R2. And so you can see the relationship here. Even though these two are the same, the ratio of these two are the same, but this and this are not the same, and this are not the same. Now, in order to work with rotational motion, you have to understand the concept of a radian. And 2 pi radians represent, so 2 times pi, or 2 times 3.14159, encompasses an entire passage through a complete circle. So if a angle of displacement or rotational angle is 2 pi radians, then it is equivalent to 360 degrees. And this is a situation where we will begin using the radian part of our calculator as well. Now the second new concept that we have to look at is angular velocity. And angular velocity, also abbreviated lowercase omega, is the rate of change of the rotational angle. And so Here you have a car that's moving at a velocity v. So what that would be is delta theta divided by t, delta t, the rate of change of the rotational angle. Now you can relate the linear velocity to the angular velocity by the following formula. The linear velocity is equal to the angular velocity times the radius of curvature. So if a car is moving at a linear velocity to the right, at the same time the tires are rotating at an angular velocity of omega. The speed of the tread relative to the axle is the velocity, linear velocity, and is the same if the car were jacked up. Thus, as the car moves forward with this linear velocity, the tires have to turn with this angular velocity, if r is the radius of curvature. The larger the angular velocity of the tire, the greater the velocity of the car, assuming, so the larger omega, a larger v is, assuming that r remains the same. Now let's say, for example, that omega remained the same, but r increases. What would happen? Well, v would increase, right? And this is exactly why people who want to get away with speeding put large tires on their car. They put bigger tires, they get the same omega, therefore on their speedometer it looks like 60 miles an hour, but that speedometer is calibrated for a 16-inch tire, and they put a 19-inch tire and they're actually going 75. And when the policeman stops them, they say, oh, I've got large tires on, so my speedometer is not accurate. And many times the police will let them go. Suppose a disc shown above, and you got a fly that's sitting there riding on this disc, and it has a radius. He's right at the radius, which is 0.3 meters. And the disc is rolling or turning with a linear velocity of 15 meters per second. What is his angular velocity? Well, here's the linear velocity. If you rearrange this so that you have now the angular velocity is equal to v over r, you put the numbers in, you get an answer of 50 radians per second. And that can actually be converted. Remember, it's 2 pi radians per full circumference, so you could divide this by 2 pi and it would tell you how many revolutions per second you would be moving, and it'd be moving quite fast actually. Now, I said before that while the speed was constant, the direction was now changing, and therefore, although the speed that the individual is moving around is the same, they are accelerating because they're throughout the movement, it's a change in direction. All the acceleration that we've been talking about up to this point is acceleration that occurs because of the change in magnitude of the speed. This is the first situation where the magnitude of speed does not change, but because the direction changes, there's an acceleration, and that acceleration is called centripetal acceleration. Since the direction of velocities change at two different points, there is a delta v, and it's related to the center of the curvature of the circle. And you can see this is the diagram that shows that. And since acceleration subscript c for centripetal acceleration is delta v over delta t, the acceleration is directed toward the center. And it's called centripetal acceleration. And here's the formula for centripetal acceleration. It's fairly standard. You have a change in omega squared times the radius of curvature, or v squared divided by the radius of curvature. And this is a formula that you should remember. The centripetal acceleration is equal to the linear velocity squared divided by the radius of curvature, or it's equal to the angular velocity squared times the radius of curvature. So here we have a car that's rounding this corner. It has a linear velocity of v, and because it's rounding this corner, it's going to have a centripetal acceleration toward the center of rotation. Suppose this car is rounding this curve, which has a radius of curvature of 500 meters at 25 meters per second. What is the centripetal acceleration? And compare that to the acceleration due to gravity. Centripetal acceleration is v squared over r. It's 25 squared divided by 500, or 1.25 meters per second squared. That divided by gravity, it's 0.128 g. So the amount of acceleration toward the center here is a little less than 0.15 the force of, or the acceleration due to gravity. So here's another problem. You have a centrifuge with the center of rotation here, and whatever's in them is right here. The center of mass is here. It's accelerating around. Its linear velocity is around the circle. It's accelerating toward the center because of its change in direction. The center of curvature, the radius of curvature is 7.5 centimeters, and it's rotating at 75,000 revolutions per minute. So what is the centripetal acceleration? We said that centripetal acceleration is v squared over r, or omega squared times r. Omega, there's 7.5 times 10 to the fourth revolutions per minute times 2 pi radians per revolution divided by 60 seconds is 7,856 radians per second. That's the angular velocity. You multiply the angular velocity squared times the radius of curvature in meters, converted to meters, and you get an angular, or a centripetal velocity or acceleration of 4.63 times 10 to the 6th meters per second square. Radians goes away, and the meters here, it takes its place in the label. Comparing that to g, it turns out to be huge compared to g, 4.72 times 10 to the 5th g. Now, if you have acceleration and you have a mass, then you have a force, according to Newton. So centripetal acceleration is associated with centripetal force, and the force is in the same direction as the acceleration. So you have, the path is this way, the acceleration is toward the center, so the centripetal force is towards the center. It is parallel and in the same direction. Centripetal force is equal to the mass of the object times the centripetal acceleration. So here you have centripetal force is equal to the mass times centripetal acceleration. Centripetal acceleration is equal to v squared r. So if you substitute v squared r, you get centripetal force is equal to mass times v squared over r, or mass times radius times omega squared. And this is a formula you should keep in hand. Centripetal force is perpendicular to the velocity and causes the uniform circular motion. The larger the centripetal force, the smaller the radius of curvature and the sharper the curve. In other words, the larger this is, the smaller this is. Or excuse me, the larger this is, the smaller the radius is to accommodate that same finding. In other words, radius and centripetal force are inversely related. Radius and velocity are directly related, etc. So let's look at a couple problems with centripetal force. And then we'll stop at this point and go on to the next part. So here's the car. It says to calculate the centripetal force on this car that has a mass of 900 kilograms. It negotiates this curve that we talked about before that had a radius of curvature of 500 meters at a velocity, linear velocity of 25 meters per second. If the curve is unbanked, what is the minimum coefficient of friction that will prevent this car from spinning out? So here is your force diagram. Your normal is perpendicular to the weight, or parallel to the weight in the opposite direction. Centripetal force is in this direction. So first of all, the calculation of centripetal force. Here's your formula, mv squared over r. The mass is 900, the velocity is 25, the radius of curvature is 500. You do the math and you get 1125 newtons. The prevention of spinning out is when these two forces are equal. So the friction force is equal to the centripetal force. And that's going to be equal to the normal times mu. If you rearrange this for mu, you end up with the force divided by the normal, which is the mass times gravity. And doing the math, you get 0.13 as the minimum coefficient of friction. If the coefficient of friction is less than that, then this car spins out of the curve. So we'll stop at this point, and then when I come back, we'll talk about more problems related to centripetal force. We'll also talk about fictitious forces and other things that occur with uniform circular motion. And we'll end up, the latter parts, we'll end up talking about Newton's law of gravity and Kepler's laws of planetary motion.